So welcome to this lecture on geometry of information. First of all, I would like to thank very much organizers for organizing this beautiful summer school and workshop, Viswa 23. My name is Noémie Combe. I've spent 5 years, it will be 5 years that I spent at the Max Planck Institute, where I worked with the Grand Maître Yuri Ivanovich Manin. So presentations being done, let's start. So I will explain a little bit about how I see things. So in this talk, using geometry, we want to describe new structures, new geometric structures or algebraic structures, and discover some hidden patterns of mathematics, for example, in information geometry. This is a very broad philosophy. This is a philosophy guiding mainly all my research, and this is what I would like to transmit in this lecture. In particular, a guiding idea is to bridge different aspects and facets of mathematics. So here, for example, we will see relations, beautiful relations between differential geometry, probabilities, and algebra. So everything will be about giving a new point of view on things and, bridging different aspects. So avant-propos, so before we start, I'll explain a little bit things. So we explore, the surprising case where using tools of differential geometry, it was actually possible to discover new emerging structures in a domain called statistics. And this led to the emergence of a new domain called geometry of information. I would like to mention that geometry of information has many applications in artificial intelligence, ChatGPT and so on, and machine learning. The strong advantage of using geometric tools is that it offers an intuitive and at the same time very visual type of understanding of the situation. So it can be very helpful in many cases. So topics and goals that I will explore during these lectures go as follows. So the main object of information geometry are the manifolds of probability distributions. And for example, one that I will be considering is the case of probability distributions of exponential type. So connections and differential geometry tools are used here to provide some statistical information, but on a more pure mathematical side, they lead and allow to reveal some hidden aspects and structures which are interesting. And this is in particular how one can find bridges between information theory, information geometry, and some other domains, for example, topological field theory. In particular, what I have in mind is connections via a kind of PDE equation named WDVV after Witten, Dijkgraaf, Verlinde, also known as Frobenius manifolds. And we can see tight bridges and that in fact they're tight connections together. So just to give a little bit of a taste of what is the topic of, the topic of manifolds of probability distributions. So one considers a measurable space, XF, and we consider a family of parametrized probability distribution on that measurable space. And as we will see at the end of the lecture, the set of all probability distributions of a given type, of given family, exponential family, whatever family we want, over finite set forms a structure of a manifold. So that's the main topic of this lecture. And now I want to explain what I want to do with that. So, and my interest goes particularly towards flat statistical manifolds of exponential type. I call them FSME in short. And so what I mean by having exponential type is that, well, the probability distributions can be rewritten in a given way. So there is this exponential of this sum minus a potential function, psi theta. So we can always rewrite them for well-chosen parameters theta and random variables x. And so that's one thing. The second is, as I mentioned it before, parametric families of probability distributions form a manifold here. And what I'm interested also in is number 3, a case when they're flat, curvature is 0. So that's 3 things I want to explore. And this will lead to a lecture because, well, I'll start from scratch, very basic knowledge, to explain the beauty of geometry behind all this. So let's be bold. What is new? So what is new is that, well, I was talking about bridges between information geometry and topological field theory. So this came in a result published in 2020 by myself and my mentor, Noémie, that flat statistical exponential manifolds are Frobenius manifolds. That means they satisfy the WDVV equation. And WDVV equation, so this gives this Frobenius manifold, which is tightly related to Frobenius algebras. And Frobenius algebras, well, in turn, are connected to two-dimensional topological field theory. So we can, I wrote the WDVV PDE equation in this square here. So the phi stands for a potential function, G is a Riemannian metric, and then that's the relation here. So a great deal of work on the geometrization of this. So the more algebraic geometry approach was developed by Riemannian and other people. And historically, it came from this hydrodynamical type of equations developed by Novikov and Dubrovin. So Dubrovin did a very important amount of works on this topic, and there are different ways of interpreting these WDVV equations. So that was a nice new step. And there are, of course, new aspects because research never sleeps. So there is new developments on the side of Poisson geometry, and very exciting things happen. So that's for very, well, future and very actual. Okay, so I decided, given that, well, this is also maybe targeting a young public, students in master degree or beginning at their PhD. So I decided to present it as a game. And the rules are very simple. So there will be exercises and levels, and the goal is to catch a maximal number of diamonds. But the exercises I've chosen are not always linearly applying what I just said. So they're kind of traps. So you have to beware of the traps and look for knowledge that I didn't say and I didn't expose in order to solve the exercises. And if you reach a number of diamonds higher than 33, then you're an expert, and we can unlock an access to some hidden sides of level 6, which is current research. So I presented it like this. So the levels go as follows. So level 0 means you're a total beginner, so you don't get any diamonds. But so level 1 will be a beginner, level 2 light experience, level 3 experience, levels 4 and 5 it's a bit more challenging, and level 6 is nightmare, because it's we realized that in the end we didn't in fact understand well, things. So it's level 6. Okay, so after this funny explanation, we can start. So the contents will go as follows. The notions for level 1 and 2, as you can see, they're supposed to be basic. So manifolds, submanifolds, charts, coordinates, tangent spaces, vector fields, metrics, covariant derivatives, connections, parallel transport, all very important to understand relation to TFT. And level 3 is a little bit more high level, so 3 diamonds, Riemannian metrics, geodesics, length and energy, and so on. Now level 4, constant curvature, sectional curvature, non-positive sectional curvature, non-negative sectional curvature. And 5, you're an expert, information geometry tools. You're an expert, but still level 6 is the nightmare, because we're investigating new problems, open questions, and sometimes things just are complicated to understand. So that's it. Now that we presented everything, let's get started. So as I said, that's the beginner level, level 1. So I thought I ought to start in a very basic way with charts and manifolds, because maybe people from information theory do not feel totally comfortable with these topological notions. So it can be useful. So let's start with, oh, and I wanted to add that all my pictures have been generated by artificial intelligence. So it's a kind of illustration of information theory and machine learning and things like that. All right. So let's start with charts, atlases, and coordinates. So this is very, well, basic. And of course, geometry and every geometric tool started with a very concrete problem. For example, Gauss wanted, well, to have a atlas, draw a map and things like that. So in cartography, origin started. And so that's why we really want to have, well, an accurate map and something which actually works. Yeah, we want to sail and we want to know the position on the sea. Well, maybe we should know a bit of spherical geometry, right? So, okay, let's start with this. So now we have, well, a sphere. So I drew planet Earth, for example, and there is an open set that I named U, an open set on this sphere. So it's in pink here. And the question is it possible to draw an accurate map of a portion of our planet? So on the left-hand side, you have this sphere, and on the right-hand side, we're drawing the map. So as you can see, the sphere is in R3, and the map is something flat, is R2, two-dimensional. And well, doing this procedure is called actually having a chart or a system of local coordinates. I want to mention also that the map is supposed to be one-to-one. That means the bijection, right? Okay, but so what does it mean that phi is going to be an accurate map? Well, the key tool is that we want to compute the length of a curve in this open set U that we outlined. Okay, so now I proceed to a very classical definition, the length of a curve. So given a curve gamma, the curve gamma will be defined from an interval from 0, 1 to our space, so or manifold or whatever. And the length will be defined by L of gamma, which is this integral of this norm of gamma dot of t with respect to dt, such that gamma of 0 is p, and gamma 1 is q. It's 2 points that we have found, that we chose. We want to go from p to q, and so that's the length of the curve. And ideally, we would like that, well, what we want from phi is that it's an accurate map, so that L of gamma is L of phi composed with gamma for any smooth curve gamma. Okay. But what if we are lazy and we want the shortest path to go from point P to Q? Then this notion leads to the notion of geodesics. So, for example, we have shortest path, L of gamma is equal to this distance here, which is this infimum of all, well, lengths, L of gamma here, such that gamma is in the open set we have chosen, and we start from point P to point Q. And this will be a geodesic, so a shortest path. Okay, so that's, we already know how to go from point P to Q using smallest, shortest path. Okay, so now we can proceed to something more rigorous about coordinates and atlas. So we have a chart. I'm not speaking of manifold yet because I did not introduce it. We will just say a set M. A chart on a set M is a pair phi U, where U is an open subset of M, so as I drew before, and phi from U to its image, phi of U, is a bijection from this open subset U to an open subset phi of U in Euclidean space, or M. So that's the chart. And an atlas is just the collection of charts such that the union here of open sets covers M. And in particular, I think the picture below is quite explicit. We have that the image, so P is a point on U, and phi of P is going to be this M tuple, x1 of P, etc., xm of P, such that the functions xi form a system of local coordinates. And so it's exactly, well, the kind of chart we have in mind. Okay. Okay, so now that we have defined this, this allows us to talk about manifolds and submanifolds and topological manifolds. Right, so a topological manifold is a topological space M such that each point P in M has an open neighborhood U homeomorphic to an open subset of an Euclidean space. So locally, it looks like an Euclidean space, in short. So here I drew the image of a sphere. It's a manifold. And well, locally, well, the neighborhood of a point looks like an Euclidean space. So that's one thing. That's about topological manifolds. Now there's something concerning the charts, and we want to define topological compatibility of charts. So two charts, let's say phi1 U1 and phi2 U2, are topologically compatible if and only if the image under phi1 of the intersection of the open sets and the image under phi2 two of the intersection of open sets are open subsets and what we call a transition map. So phi 2 composed with phi 1 inverse defined on this formula is a homomorphism. Yeah. So that's the topological compatibility of charts. And now third, an atlas is a topological atlas if and only if any two charts in this atlas are topologically compatible. So that's about topological manifolds. And now we want to define the notion of smooth manifold. So little question, is this space, so I drew a kind of flat two-dimensional mountain, is it a smooth manifold? So let's discuss this. Yeah, I wanted to draw something. So is it a smooth manifold? Well, I would like to point attention on the fact that there's something weird happening here, right? It does not look smooth. So I have not defined smoothness yet, but smoothness is related to differentiability. And in particular, I will define it now. So if we take an open set in Rn and in Rm, so U and respectively called V, a map F from U to V is smooth if and only if it is infinitesimally differentiable. That means all partial derivatives, here, outlined here, exist and are continuous. Okay? And so now there's a tool which is very useful and which will be very much used is the Jacobian matrix. So consider two open sets, U in Rn and V in Rm, and consider a map which is smooth from U to V. Then, if we want to take the derivative of f at a given point x, we have a linear map, and this linear map is represented by what we call Jacobian matrix, and that's the matrix I outlined here, partial fi over partial xj. So that's the matrix. That's very important actually. And so let's go back to charts. So M is still a set because, yeah, it's still a set. And we want a chart, so it's a pair U phi. U is a subset of M, and phi is a bijection from U to an open subset in Rm. Okay, then two charts are smoothly compatible if and only if, first of all, phi 1 of the intersection of the two sets and phi 2 of the intersection of two sets are both open in the Euclidean space, Rm. And secondly, the transition map, so it's again phi 2 composed with phi 1 inverse, is this time a diffeomorphism, okay? So that's the notion of smoothly compatible. All right, so we have a little bit of a view now on manifolds and charts. We will talk about submanifolds, and this is a notion I'll come back to often because it's not so trivial as it seems. So a subset M in Rk is a smooth M-dimensional submanifold of Rk if and only if every point P in M has an open neighborhood U in Rk such that the intersection of U with M is diffeomorphic to an open subset in Rm. Okay, M is the dimension of capital M. Okay, so a diffeomorphism phi from this intersection into omega is called a coordinate chart of M. So this has not changed much since the previous slides. However, its inverse, psi, which is the inverse of phi, so from omega to u intersected with M, is called a smooth parametrization of the intersection of u with M. If M is a non-empty smooth m-dimensional manifold, then M is smaller or equal to K. So there's a very important tool here for, well, when we want to prove, and specifically for the exercises, it's important to know the following. So let's discuss it. So if we consider U in the Euclidean space of dimension K to be an open set, and F is a smooth map from U to an L-dimensional Euclidean space, RL. An element in RL, denoted C, is called a regular value of F if and only if, for all P in U, we have the image of P under F is equal to C, implies that the differential of F to P from RK to RL is surjective. If it is not, then C is a singular value of F. And now this is why it is important, because of the following. It's actually a theorem, although I didn't write it. So if C is a regular value of F, then the preimage F inverse of C, which is the set of P and U such that F of P is equal to C, is a smooth submanifold of dimension K minus L in the K-dimensional Euclidean space, RK. And furthermore, so this is just extract, of course. I could not say everything, but another theorem that I highlight here is that if we consider M in the K-dimensional Euclidean space RK, it's a smooth m-dimensional manifold, and if we take now a point P in M and an open neighborhood of P, if we consider F from U to R K of dimension K minus M to be smooth, such that there is 0 is a regular value, and we have the condition U intersect with M is equal to F inverse of 0, then we can define the tangent space at the point P to M. And this is the kernel of DFP. So that's actually a key tool in, well, many things we want to prove. So that's, I think, a very important theorem. And so here come the exercises. So, so one exercise that I like very much is the first one here. So prove that the special linear group is a smooth submanifold of R n times n. So we have the special linear group corresponds to those matrices, group of matrices of determinant equal to 1. And that's a smooth submanifold. And so I can give you a hint that one has to use this tool. And I have a question. Then is the set here of M defined by the xy's such that x times y is equal to 0, is it a submanifold of R2? So this usually looks, well, just two lines intersecting. So we have this line here. So that's the x-axis, y-axis, that's 0. And we have this here. And is it a submanifold of R2? Well, exercise to do. And hint is also to use this important tool. Right, so that's that was level 1. And now we can go to level 2. So level 2 is about vector fields, tangent space, flows. Okay, so we can now move to level 2. And it's about tangent spaces. So now we have introduced the definition of smooth manifolds. So let M in the Euclidean space Rn be a smooth manifold. And let's fix a point P in M. A vector V in Rn is called a tangent vector to M at the point P if and only if there exists a smooth curve such that gamma 0 is equal to the point P and gamma dot of 0 corresponds to, well, is it identified to the vector V. So this allows us to define a tangent space at a given point P. The set of tangent vectors of M at P is defined as gamma dot of 0 such that gamma, so it's a curve parameterized by R into M, or interval, it is smooth, and gamma of 0 has to be equal to B. And that's the tangent space of M at P. So a little bit more advanced question. So that's 2 diamonds, worth 2 diamonds. What is the tangent space to the space of positive definite matrices? Maybe I should recall definition of space of positive definite matrices. So that's not right yet. Excuse me. So it is a set of matrices equal to its transpose, and I'll just write that P is positive, which means that this is satisfied here. So that means this. And the question is, well, what's the tangent space to that kind of space? There was a question. I'll answer later. Yeah, so that's one question. And the second is, what is the tangent space to SLN-R? Well, here I can give a hint. And the hint is to use the important tool discussed previously. So here, there's a theorem, which is important. And yeah, and this allows to grab 2 diamonds. I'll just erase all this. Okay. So, well, at the end, maybe of the first hour of or today's lecture, you can tell me what's your guess or what's your answer to the questions I have scattered here. But yeah, and SLNR, well, we met it before, so it's this group of matrices with determinant 1, and what could possibly be the tangent space to this. I think it's really beautiful objects and questions to consider, so I'm looking forward to your answers. Okay. And without mentioning that positive definite matrices have a great number of applications ranging from medicine to machine learning and passing through all sorts of geometry tools. So yeah, very interesting. Right. Okay, so we can now move to the notion of derivative. So M is our favorite m-dimensional smooth manifold in our favorite Euclidean space RK. And F is a smooth map from M to Euclidean space RL. So the derivative of F at a point P is the map, which I'll define below. So we take a vector V in TPM, tangent space at point P, and we choose a smooth curve gamma indexed by R in M, satisfying the following. So we have gamma of 0 is the point P, and gamma dot of 0 is the vector V. And now we want to define the vector dfPV here as follows. So it gives, yeah, this limit is h tends to 0 of f of gamma of h minus f of p over h. And there's like a remark we should highlight that, well, we have to prove that this is well defined, right? So that means that the right-hand side of the equality above depends only on the tangent vector and not on the choice of a curve, yeah? So that's the derivative notion here. So yeah, I introduced it. It's more kind of analytical here, but comments, and so for advanced people, 3 diamonds, more sophistication can be reached using a more abstract language of vector bundles, tangent bundles, and here and later on, yes, and yes, that's for the moment what I wanted to say, that there is maybe more algebraic beauty if you use vector bundles, but I wanted to keep it simple, so I'm not introducing it here. Okay, so we can talk about property of diffeomorphisms. So M is your smooth M manifold, your favorite smooth M manifold. N is someone else's favorite smooth N manifold, n-dimensional manifold. They're not empty. And we have F, a map from M to N, which is a diffeomorphism. Then if we suppose that M is equal to N, then the derivative dfP from tangent space to M at P to tangent space to N at the image f of P is a vector space isomorphism with inverse defined for any point P in M. So why am I saying this? Well, because actually it leads, so I was talking about submanifolds, so there was one kind of easy to guess definition of submanifolds, but now using, well, entire range of different aspects of these maps F, we can actually define submanifolds in a different way. So one I would call a bit evident kind of definition is that if you have M in the Euclidean space Rk of dimension M, it's a manifold. And if you consider a subset P and M, then you can call it a submanifold of dimension N, if and only if P itself is an N manifold, right? This is kind of clear. But now we can mention a few other things. So we have M is still this M-dimensional smooth manifold, and N is an N-dimensional smooth manifold, and we have a smooth map, F from N to M. We say it's an immersion if and only if its derivative is injective for any point Q in N. We say that this map is proper if and only if for any compact subset K in F of N, well, the preimage of K under F is compact. And last, the map is an embedding if and only if it is a proper and injective immersion. So this kind of encapsulates everything above. Okay, so let us now go back to our mantra about submanifolds. So M, as previously, is a M-dimensional manifold and an N-dimensional manifold. F from N to M is an embedding. If this is the case, then F of N is the submanifold of M. Okay. Again, if P in M is a submanifold, then the inclusion from P to M is an embedding. And third, maybe I could draw something here. Let M be an M-dimensional manifold. Subset P in M is a submanifold of dimension N. If and only if, for any point, let's draw P0, P, so that's the point P0. There exists a coordinate chart, so that's what I drew. Up, that's you. Phi to Rm on an M open neighborhood of U of P0, such that the image of U intersected with P, so it is dashed here, is equal to phi of U, so its image intersected with Rn times 0. It's maybe a little bit more difficult to imagine than previously, but maybe with a drawing it helps a little bit better. Okay. And now exercises. So let's catch diamonds. So consider the map F from S1 to R2, which is defined by this equation. So X is mapped to itself, X, and Y is mapped to XY. So question is it a proper immersion? Is it injective? And now second question is, consider the map F from R to R2, which is defined by Ft is mapped to T2 T cubed. So is it proper? And again, the same questions. Is it injective? Is it an embedding? So this is a very classical object in algebraic geometry. There's cusp kind of curve. Looks like this. Well, picture is not right. Yeah, but it's very standard in algebraic geometry. Curve. Okay. Right. So we can discuss the exercises later. And well, I can talk about vector fields and flows. So keywords are vector fields and manifolds, flows of a vector field, well, flow of a vector field, and it's tightly related to group of diffeomorphisms. I won't talk much about it, but it's very present. And of course, Lie bracket of two vector fields. Okay, so about vector fields and flows. So here I wanted to say that actually the language of bundles, tangent bundles, quite well, to my taste would be a little bit more adapted perhaps for the notion of vector fields, smooth vector fields, but maybe it's just a question of taste. So let's start. So M is a smooth m-dimensional manifold, still in Euclidean space. And we define a smooth vector field on M as a smooth map denoted capital X from M to RK, and such that X of P belongs to TPM, the tangent space to M at point P for any point P and M. The set of smooth vector fields on M is denoted by the following. So I chose to call it vect of M. It is defined as the set of smooth vector fields X from M to RK, where X is smooth, and X of P belongs to the tangent space to M at P for any point P in M. Okay. So, okay. First question. So prove, that's question to you. Prove that the set of smooth vector fields on M is a real vector space. Okay, so that's one question. Now let M be the two-dimensional Euclidean plane. A vector field on M is any smooth map, X from R2 to itself. And we could take, for example, X of xy defined as X and minus Y. So the question is, how many zeros does this vector field have? Okay. And a slightly more complicated question, prove that every smooth function f from Rn to R determines a gradient vector field. So this requires maybe a bit of notions that I did not explain here, but it's good to have an idea that this exists. Yes. Okay. So we can proceed to integral curves. So let M be a smooth m-dimensional manifold. And take X to be a smooth vector field on M. and take an open interval I in R. A continuously differentiable curve, gamma from I to M, is an integral curve of x if and only if gamma dot of t is x of gamma t for any t in I. So I maybe leave a few seconds to imagine it. Otherwise, we can go back to the slide at the beginning about, well, the very first slides for the curves. So x is defined along this curve here, this vector field. Right. And now, okay, so this is one thing. Actually, I could draw the arrows, so I didn't draw everything. So that could be a vision of x of gamma t here. Okay. Now we develop a little bit more this definition. So M is a smooth m-dimensional manifold. And X is our smooth vector field on M. Then there exists an open interval I and R containing 0 and a smooth curve gamma parametrized by this open interval I into M, satisfying the equation. So I called it equation 1. Gamma dot of t is, well, this vector field x along gamma of t, along the curve, such that gamma 0 is fixed at p0, and the equality holds for any parameter t in the open interval I. Okay, so there is actually a strong assumption of unicity. So suppose that we have two solutions to the equation 1. So suppose we have two possible solutions, being the curve gamma 1 and gamma 2, and they must both satisfy condition star. That means that the interval I contains 0. Well, then it just turns out that they cannot be distinct, these curves. They have to coincide. So we have a unicity type of assumptions. Gamma 1 of t is equal to gamma 2 of t for any t in the intersection of I1 with I2. So many people think of these vector fields and flows as some kind of water which is flowing down on, for example, a donut, or you can imagine putting a donut in some chocolate, and then it's like you have a vector field and integral curves. So that was for the intuitive picture. Right. So this allows us to move on to the notion of flow of a vector field. So we consider a manifold, for example, a torus, so a donut. And we have a vector field x, which is smooth on this donut. Then we have two things happening. So for a point P0 in M, the maximal existence interval of P0 is the open interval defined as follows. So it's a union of all intervals in R, open intervals in R, containing 0. And there is a solution gamma of 1. So 1 was just the previous equation, 1 in red. Gamma dot of t is x of gamma t, with gamma of 0 equals to P0. Okay, so we have this maximal existence interval, union of intervals containing 0, and such that gamma from I to M is a solution to the equation we considered. So once that this is settled, it allows us to define the notion of the flow of this vector field x. And the flow of this vector field x is the map. We defined it, so I defined it here, phi from, well, an object called D into the manifold. And this object D is defined as the set of pairs T P0, where P0 belongs to M, it's a point at M, and T belongs to the parameter, the maximal existence interval, IP0. So this looks slightly complicated, but actually it is not so complicated because it's just a question of notation. So now below on the last line, it's much more clear what is meant by this. We have phi of two things, t P0. T is, you can think of it as a time. P0 is a point, so it's something on a manifold. And this is defined as gamma t, it's this curve, where gamma from IP0 to M is a unique solution of equation 1 that we met on the previous slide here. I'm gonna check. Yes, perhaps it is a good moment to make a break because we did, I think, an hour or so. So you can think during this time about the exercises, and then we'll proceed to the next part, which has to do with group diffeomorphisms. And yes, we'll be back maybe in like, I don't know, 5 minutes or a bit more, 5 to 10 minutes. Okay. All right, welcome back. So we will talk about the group diffeomorphisms. It's the last topic of this level. So as I said, there's a deep range of well, group diffeomorphism theory related to those vector fields, and so that's what we're going to mention very briefly, though, but it's a very important topic actually. So let us denote the space of diffeomorphisms of M as follows. So diff of M is the set of diffeomorphisms phi from M to itself, as simple as that. And 2 diamonds can be gained if we prove that this is actually a group. So a group operation consists of composition and a neutral element, which is the identity, composition and of course inverse. So yes, up to you to prove that this is a group. And now we have also the notion of a flow, which interferes here. So the flow of a complete vector field is a group homomorphism from R to the space of diffeomorphisms, diff of M, such that at a given time t, you map, well, phi t. Phi t of is phi of t p for a given time t, and p is an m. So I just remind that phi t p0 has been denoted here. Just here. Okay, so that's just a curve actually. Phi t p0 here. Okay, and this homomorphism is smooth and characterized by the following equation here. So, so we have to do a derivative with respect to t of phi t of p, and this is, well, this vector field x of phi t of p, and we impose that phi 0 of p is just p. So that's basically what it is about. So it's a very rich topic. I will not mention too much here. And actually for 3 diamonds, you can investigate the notion of isotopy. So that's more of topological theory, and I would say that historical papers were written, for example, by Epstein. But the story goes as follows. So we have, like, for example, 2 points, P and Q. And let's say that we have a curve here. Well, the isotopy will be just essentially deforming this curve. So you could go like this. And they're all isotopic, right? There's a family of kind of deformations. So that's about isotopy. I will not mention it here today. But that's strongly going to be related. There's a group of diffeomorphisms acting there. Okay. So that was to close this level. So that was level 2. It was light experience called. And now level 3 is, well, we start to have experience, and it's going to be a little bit tougher. So it's about covariant derivatives, parallel transport, and connections. But before, there is a small notion that we could have mentioned before. It is about the pullback of vector fields. So pick your favorite m-dimensional manifold, M, in the Euclidean space. It has to be smooth. And N is another smooth manifold of dimension n. Suppose that we have a smooth vector field X. So if we have a diffeomorphism denoted phi from n to m, then the pullback of this vector field X under phi gives a vector field on n. So we can, let's draw it. So if we go from n to m, that's m, for example, here. And phi is this map, the diffeomorphism. And we have X as a smooth vector field, then the pullback of X under phi is a vector field on n, defined as follows. So X is living somewhere here, and we are pulling it back on n. Okay, so it allows to actually transport, if we have 2 manifolds, to transport a vector field living on one manifold onto, well, the other one, but under the condition that you have phi, which is a diffeomorphism. And so this is given by this formula on the last line. Erasing it. Okay. And this allows us also to mention Lie brackets. So if M is a smooth m-dimensional manifold, and if we consider a pair of smooth vector fields X and Y, then actually there exists, we can compute the Lie bracket of X and Y. And it's a vector field given by the bracket xy, and defined as follows. So bracket of xy at p is this differential of x at p yp minus, well, it's just Leibniz kind of formula. And so that's one thing. And the second one is that, well, now we can go a bit more deeply about the flows, concerning the flows of x and y. So we are imagining that we're parametrizing, well, the time is on the line r, and we have diffeomorphisms of m, so t is mapped to phi t, and the second one, t is mapped to psi t, corresponding respectively to x vector field and y, the other vector field. And now if we fix a point P in M and we define a smooth map gamma from R to M as follows, that means gamma of T is defined as the composition of phi T with psi T with phi T inverse, psi T inverse at P. Then we have that the derivative of gamma at 0 is 0, and derivative with respect to t for when t tends to 0 of gamma square root of t gives this formula dxpyp minus dypxp. So that was to explain how this Lie bracket, where did this come from actually? So it's a small lemma explaining how we managed to arrive to this Lie bracket story just above. And so now we can mention a bit some relations. So if M is in the Euclidean space Rk and N is in Rl, smooth manifolds, X, Y, Z are smooth vector fields. Now we need our diffeomorphism from N to M. Well, then the pullback under phi of the bracket will give a bracket of the pullbacks. So pullback of xy bracket is the bracket of pullback of x and pullback of y. So in some sense, it is conserved. So we conserve under this pullback for phi being a diffeomorphism, the vector fields and the bracket, the Lie bracket. And then I recalled some, I think, classical notions about Lie brackets. So we have this relation bracket of xy is equal to minus bracket of yx, that you can write as I wrote here, bracket of xy plus bracket of yx. And the Jacobi identity, so a relation reminding a bit of some co-cycle relations, so bracket of x with bracket yz plus bracket of y with bracket of zx plus bracket of z with bracket of xy. And this is all supposed to be equal to 0. The sum is equal to 0. So these are the important relations about the brackets occurring for these smooth vector fields on M. All right, this being said, we can proceed to covariant derivatives. So this is going to be a little bit more complicated. And Levi-Civita connection. This is actually very interesting part, very useful part of differential geometry that will apply definitely into information theory. Right. So take your favorite smooth m-dimensional manifold M in Euclidean space Rk. So we recall something that is, I think, clear, that each tangent space can be identified to some m-dimensional vector space in this context. I mean, any two tangent spaces, TPM and TQM, where P and Q are points on M, are isomorphic. So picture, so M is the manifold, and we have tangent space here at a point P, and tangent space there, TQM here, and well, it sounds like they're going to be, well, we think it's going to be isomorphic. However, be careful that there's no canonical isomorphism from TPM to TQM. And this is where the entire beauty of covariant derivatives and parallel transport shows up. So in particular, every smooth curve in M, so we can draw it, joining P to Q, induces an isomorphism between tangent spaces via parallel transport of tangent vectors along that curve. So that's why we introduced vector fields previously, because in fact, we're going to use all of this, all of our knowledge introduced before for this covariant derivative story. Okay. Just erase it maybe like this. Nope. Okay. So let's begin. So, but some facts about covariant derivatives. So there are two things that we're going to have to mention, which are, well, the first fundamental form and the second fundamental form. So first here and second. And that will be important actually for our work. So let M be a submanifold of an Euclidean space. The inner product on the ambient space, so it's what I wrote here, determines an inner product on each tangent space. And this is given by what we call a first fundamental form. So the inner product, well, the classical one that we know for Rn here, this inner product will be, in some sense, projected for the tangent space. Okay? That's the first fundamental form. And the second fundamental form is obtained by differentiating the map, which assigns to any point in M, so any point in M, that is M, the orthogonal projection of the derivative of a vector field along a curve. So orthogonal here, yeah. Orthogonal projection. So that's two things that we will study. And now we can talk about covariant derivatives. The covariant derivative of a vector field along a curve is the orthogonal projection of the derivative in the ambient space onto the tangent space. And so that's why we need these first and second fundamental forms, at least to, well, see them. And okay, so now as a consequence, the covariant derivative gives rise to what we call parallel transport. And the covariant derivative is determined by something which is very much used, the Christoffel symbols in local coordinates. Okay. I'll erase this. This. Okay. Very nice. So let's talk about the first fundamental form. Suppose M is again an m-dimensional submanifold of the Euclidean space. It is smooth. The inner product on the ambient space determines an orthogonal projection of the Euclidean space onto the tangent space. The first fundamental form on M is the field, which assigns to any point P in M the bilinear map described here. GP maps TPM times TPM into R, and this is defined by, well, the equation here. For any vectors V and W in the tangent space. Okay, let's continue. Let M be again a smooth manifold, submanifold of the Euclidean space of dimension M. The inner product on the ambient space determines an orthogonal projection of Rn onto the tangent space for any P. And this projection, we will describe it, represent it under the shape of a matrix that we call here pi of P. So it's a matrix, it lives in this space here. And it is uniquely determined by the following condition. So it's an orthogonal projection. So I think it is clear that we need to require these equalities. So pi of P is pi P squared, which is equal to pi P transposed, and such that pi of V equals to V. So it's a kind of identity if and only if the vector lives on the tangent space for any point on the manifold and any vector in Rn. So this should be N here. Okay. So actually it's very important to understand this matrix, this orthogonal projection, because it will appear for the covariant derivative and for the second fundamental form. Okay, so let's define the second fundamental form. So as we said at the beginning here of the level, we were saying the second fundamental form is obtained by differentiating the map, assigning to each point in M an orthogonal projection of the derivative of a vector field along a curve. So that's what we're defining here now. We have a collection of symmetric bilinear maps, let's call it HP, which goes from the Cartesian product TPM times TPN into the orthogonal space, TPM orthogonal. And this is defined by, like more precisely, HP of VW for two vectors in the tangent space V and W as the derivative of the differential, of pi at the point P of V and W. And that's the second fundamental form on M. So here I outline three exercises for 3 diamonds. Well, it's one exercise actually. So it's very interesting. I think very enlightening here. So consider an Euclidean space of dimension n. And we know that it can be splitted, okay, Cartesian product, into subspaces, one of dimension m and the other one of dimension n minus m. Now, let's take M, a smooth manifold in Rn, such that the point, we choose a point equals to 0 without loss of generality. And now we consider two things. The tangent space at 0 of M is equal to Rm Cartesian product with 0, so it's at a kind of 0. So how could I draw it? Let's say this is Rm times 0. And the orthogonal is going to be, well, what is orthogonal? So let's draw it in a different color, green. It's going to be T0m. Orthogonal is 0 times Rn minus m. So it's going to be the complementary part. So I did not mention the implicit function theorem, but it exists by some given theorem. There are open neighborhoods of 0, so 0 was here, which I call omega for Rm and V in its complementary part, such that the map from omega to V is smooth and has V of 0 equals to 0. Furthermore, we can check that the differential of f at 0 is again 0. So the aim is to show that the second fundamental form is given by HPVW is 0, comma, and now we have this second derivative of f with respect to xi in xj direction. So that reminds us a little bit of Hessian geometry appearing here. Okay. So I think it's kind of a little bit enlightening to spend time looking at this exercise here. So it's really kind of, well, explaining, well, what it means exactly to have this, well, inner product determining an orthogonal projection onto the tangent space. It kind of shows a bit what's happening here. All right. So we can move a little bit further. And we can talk about covariant derivatives. Okay, so we consider an open interval in R. So it's our parameter time, which parameter is our smooth curve. Gamma goes from I to M on a given manifold. A vector field along that curve is a smooth map, such that x of t belongs to the tangent space to M at a given point gamma of t for any t in I. Yes, so we have a curve and we want to define a vector field along that curve. And we know it's going to give a smooth map by the definition, and that any vector of this vector field belongs to the tangent space to M at a given point of the curve. Now, the set of smooth vector fields along the curve is a real vector space. That was one of the diamond exercises. So it's a real vector space, which I called vector gamma. And now comes the important notion of covariant derivative of x. So the covariant derivative of x is the vector fields denoted nabla x in this vector space, real vector space, vector gamma, defined as follows. There's the formula in pink, nabla x of t, and we're going to use actually this projection pi. So we defined it here, the projection represented by the matrix. So an orthogonal projection of Rn into the tangent space along the curve gamma, and we need the derivative of the vector field x dot of t. Okay, so we're going to, so where pi of p is this map, pi from M to R n times n, matrix representation of the orthogonal projection of Rn onto the tangent space. And we need to take the derivative of this vector field. So abstractly, covariant derivative is something like that. So I illustrated this vector field. Yes, a vector field along a smooth curve on a manifold M. Yes. So that was so that's the covariant derivative. So that notion is quite important, is in fact crucial, yes, and leads to the notion of parallel transport, which I discuss in the next slide. Right. So let's talk about parallel transport. I will start first by introducing the notion of a parallel vector field. So consider an open interval in R, and consider a smooth curve in your manifold M, parametrized by I. A vector field X along gamma is called parallel if and only if nabla of x of t is 0 for any t in the interval I. Let's recall what nabla x of t. Nabla x of t is on the right-hand side of the slide, is the pink formula here. Nabla x of t is this pi gamma of t x dot t. Is this covariant, it's this formula, covariant derivative. And I have an example. So suppose M is an Rn, and suppose M, the dimension of the manifold M, is equal to n, so that M forms an open set in Rn. Then a vector field along a smooth curve is a smooth map defined from the interval I into the Euclidean space Rn. Right, because we chose M to be equal to n and M to be just an open subset of Rn. Well, then the covariant derivative is equal to the ordinary derivative. Nabla x of t is just x dot of t, because we didn't need to project anything. And so this conclusion means that nabla x of t is 0. So x dot t is 0. But that is true if and only if we have a constant. X is constant. Okay. So that's an example. So now let's talk about parallel transports along curves. So suppose I is an open interval in R. And suppose that this interval parametrizes a smooth curve on the manifold M. So for 2 points in I, time t0 and time t1, we define the map capital Phi, which maps the tangent space at a point of the curve at time t0 in M to a tangent space to M at a point on the curve at time t1 or t. And phi is just a fancy notation. Phi gamma of t, t0 is just a fancy notation of defining x of t, where x is just a vector field along curve gamma. So this map is the unique parallel vector field along gamma, satisfying x t0 equals to v0. And so the collection of maps phi gamma t t0 for any points in I, t0 and t1, or t0 and t, is called a parallel transport along gamma. So you're just transporting parallelly your vectors along the curve. And so this notion is actually crucial when it comes to curvature, for example, and holonomy. Okay, so let's discuss some properties. Let I be an open interval in R, and gamma a smooth curve in M, parametrized by I. The map phi gamma ts from the tangent space to M at the point given by gamma s, mapped into the tangent space to M at the point gamma of t, is linear for all st and I. For any elements are st and I, we have a composition relation. Phi of ts composed with phi of sr is just phi of tr. It's a transitivity relation. And naturally, phi of t, so we didn't move much, right? We go from t to itself. Well, it's just the identity, naturally. And furthermore, now if we take 2 points st and I, well, two times, and vw are vectors in the tangent space, then we have the following purple relation. And last, for any vector field x along the curve gamma and 2 parameters t, t0, and I, we have an interesting relation here. We have the following interesting relation, which I have outlined here. So it's essentially the same, taking nabla of xt, defined here previously, and taking the derivative with respect to t of phi for the vector field X. Okay, so that was a synthetic vision of parallel transport and covariant derivatives. There is a tool which is very useful, which is the one of Christoffel symbols, and which actually allows to, well, describes geometry, well, of covariant derivatives. But you need local coordinates, so that's maybe a bit of a disadvantage in some sense. So the goal is to examine covariant derivative in local coordinates on some embedded manifold M and Rn of a given dimension. Let me explain what's happening here. So I did a picture on the upper side of the slide. We have M, a manifold in Rn. And I did a picture of the coordinate chart. So we're working just in local coordinates. U is an open in M, phi is this chart, and psi is going to be its inverse, the inverse of phi. Omega is the image under phi in the Rm. So that's the setting. We take this coordinate chart phi. And now we consider a point P in M and in U. P is going to be the image under psi. Psi is the inverse of a given point X in omega. So if P is equal to psi of X in U, the tangent space of M at the point P is the image of the linear map differential of psi from Rm to Rn. So it is a property I did not prove previously or did not mention, but it exists. Let us discuss it more. A pair of tangent vectors can be written as follows. So, as we said, the linear map differential of psi, well, gives an element in tangent space. So V, let V be such a vector. V is equal to d psi x of d psi of psi. And in local coordinates, we can write it as psi I partial psi over partial xi. And we can take another vector, which will be very similarly defined, like on the second formula of the fourth line, where psi lives in Rm and eta also lives in Rm. Okay, so the restriction of the inner product in the ambient space in Rn to the tangent space is, as we have already said, given by the first fundamental form. So we had this bracket of V with W, this inner product, and this is defined in local coordinates by the equation I wrote here, such that the functions g and x by ij are mapping omega into R, and they are defined by this relation inner product, partial psi for partial xi and the other direction xj for any point in omega. So that's the local setting. We're talking about local coordinates. Yes. And so now we want to know exactly how is it possible to express, well, we still did not define the crystal symbols, first of all, but we want to understand how we can express concretely something, well, expressing this covariant derivative. Right. So now it becomes a bit technical. Let C be a curve in omega and define an interval I in R. And consider the curve gamma, which is the image under psi. I recall that psi is the map from omega to U. The image of this curve C, which was defined in gamma. So we can make a picture, add it on the picture here. Oh, sorry, doesn't work as expected. Too bad, no picture. Okay, so, but let's just imagine it that we had a curve in omega C and its image under psi is gamma and it lives in U, in M. And now take a vector field along the curve gamma. This is denoted by X as usual. Then this vector field X of t belongs to this tangent space to M at a point of the curve at gamma of t. And this is the image of this differential of psi at ct mapping Rm to Rn for any t and I. That's one thing. So in particular, what we can say about this is that there exists a smooth function, let's say psi from I to Rm, such that the vector field x of t can be expressed, which can be expressed as the differential of psi d psi at ct, psi t. We can now take its derivative, so x dot of t. That's the purple big equation. So it's just a question of writing down the definition of a derivation. We still did not find the crystal symbol here. So we need to discuss a bit furthermore. So examine the projection, so this nabla of xt given by this projection pi along the curve of gamma t, evaluating x dot of t. And let's discuss it now. So the first summoned is in fact tangent to M. Okay, and the second lies, in fact, in a tangent space to M at psi of x, at the point psi of x. Well, so in other words, it means that it's expressible also using a basis of partial psi over partial x. Okay, so what we want to modify is going to be this second summand. In particular, what do we want to say is that expressing it in this basis, partial psi of partial x, xk, is going to allow us to introduce some coefficients which are smooth functions, which are denoted gamma ijk. So all this right summoned can be expressed just using the sum of gamma ijk and now the vectors generating the tangent spaces, meaning partial psi over partial xk for any ij ranging from 1 to m. So going back to the formula, the purple big formula, it becomes well, an exercise perhaps to rewrite nabla x of t as the sum. So the first summoned was x dot psi dot partial psi. So psi is just on the right hand side, and now we just replace what we wanted. So the second summand in terms of this basis partial psi. And so that's how we gain the gamma ijk coefficients, well, the smooth functions here. And so welcome to the Christoffel symbols. Gamma ijk are called Christoffel symbols. So yes, so we've done a great job now. We can express a lemma, which is also very helpful and useful. So let omega in Rm be an open set, and G indexed by ij smooth functions such that the matrix is symmetric positive definite. Consider gamma ijk to be smooth functions. Then gamma ijk satisfies the symmetry condition. Gamma ijk is equal to gamma ji for a fixed k. And we have partial relation, partial of jil over partial xl is the sum, a sum which is expressing gil, a relation using gil and Christoffel symbol, but if and only if gamma ijk is given by the last formula, that means expressed in terms of j. So that's actually a very important lemma, to use. Right. So I think I should stop here because then we're moving to higher level. So I'll leave it for Thursday. Okay, so welcome back to lecture 3 on geometry of information. I'll just make a quick recap about what happened previously in lecture 1 and 2. So last time we were acquainted with charts, manifolds, vector fields, flows, and we got to a higher level of covariant derivatives, parallel transport, and connections. So this means that today we'll present metrics, curvature, and discuss applications to information theory. And then if we have enough gemstones, collected enough gemstones in the exercises, well, we can perhaps unlock some hidden aspects of level 6, which is about connection to topological field theory. So let's get started. So we're going to talk about metrics and curvature. And I will start with the notion of Riemannian metrics. So M will be always denoting a smooth m-dimensional manifold. So let M be our smooth m-dimensional manifold. A Riemannian metric is a collection of inner products, which are T from the tangent space to the manifold M at a point P, so TPM times TPM, into R. So for two vectors V and W, I associate, well, something that I denoted by G indexed by P for the vectors V and W. And that's possible for any point P on M. We require, furthermore, that the map, which assigns to any point this inner product, is smooth for every pair of vector fields x, y in what I denoted the space of vector fields vector M. Now, a smooth manifold equipped with a Riemannian metric is called a Riemannian manifold. So that was a very short introduction about Riemannian metrics. Let's see where this leads us to. Well, there's a very important notion called the Levi-Civita connection. And this, why is this important here? Because it will appear as an extension of the notion of covariant derivatives for a Riemannian manifold. So we had seen a definition of covariant derivatives in a very, well, Euclidean setting. We didn't have much assumptions. Here we want to explore this definition, but for the case of a Riemannian manifold. So that's what we're doing, extending the idea of covariant derivatives to any Riemannian manifold. Okay, so this being said, suppose that we have a Riemannian manifold, M with its Riemannian metric G. There exists a unique collection of linear operators, nabla, which are mapping the space's vector fields along a curve gamma into itself. That's called the covariant derivative. And there are a few rules now, axioms. So first of all, there's the Leibniz rule. So for any smooth curve gamma on M, gamma is indexed by, well, parameter space or time, as you want, from I to M. And we have any kind of smooth function lambda from I to R. Furthermore, let us take a vector field X. Then we have the following. Nabla of lambda X is lambda dot X plus lambda nabla X. So this is the Leibniz rule. Secondly, we have a chain rule. So given a curve C and a curve gamma, we can define nabla of X composed with C, and this gives this formula number 3 here in the middle of the slide. C, I recall, as a smooth curve from I to omega, and omega is an open in Euclidean space Rn. And here, nabla Ix is a covariant derivative of X along the curve. So Xi is mapped to gamma X, and it is thus a smooth vector field along gamma. So that's 2 axioms. We have 2 more, one that we could call a Riemannian property. So for any vector field along the curve gamma, X and Y, the derivative with respect to t will be splitted in this sum, actually, on the second line. And finally, a last property is that it is torsion-free. So there are many ways of expressing it. One of them is how I wrote it here. So for any interval I and j, which are open in the real line, and any gamma, which is smooth from the Cartesian product of I with G into M, we can denote nabla as the covariant derivative along the curve S mapped to gamma st. T is a fixed time. And by gamma t, the covariant derivative along the curve, which maps t to gamma st, where this time S is fixed. And so you can see that we can swap S and T in the last formula on the last line. So that's being torsion-free. So this is more or less a very abstract list of well, properties that are necessary. And so now we can introduce it as a formal definition, which is much more way everybody defines it. So let's start. The Levi-Civita connection is the unique affine connection on the tangent bundle of a manifold preserving the Riemannian metric, and we have torsion freeness. So yes, so as I said, we wanted to extend the notion of covariant derivatives, well, for Riemannian manifolds. So there's a comment here about this. For Riemannian manifolds, the term covariant derivative is often used for the Levi-Civita connection. So now more formally and more in a more concise way, we can say that an affine connection is a Levi-Civita connection if nabla G is 0. And nabla G is 0 is often called in the literature as being compatible with the metric, compatibility with the given metric G. And torsion freeness can be very nicely summarized by this last formula, nabla x of y minus nabla y of x is just simply the Lie bracket x, y. So that's now summarizing everything we said before in 2 words. So that's the Levi-Civita connection. All right, so well, before we go further, let's talk a bit about geodesics. So as we said at the very beginning, the geodesic is related to the notion of a shortest path. So for example, if you're skiing in a mountain, well, you want to find the shortest path, perhaps to win a competition, to be the fastest, or I don't know, whatever, or you don't want to be too tired in the end, so you're looking for the shortest path. Right, so the concept of geodesic, in fact, generalizes the concept of a straight line in Euclidean space. And so we were talking about geodesics in lecture 1. Here we're going to talk about them in the context of Riemannian manifolds. So keywords that will be mentioned here are geodesics in Riemannian manifolds, introducing geodesics as extremals of the energy and length functionals, and characterizing them as solutions of a second order differential equation. So that's about geodesics. So we're revisiting the notion we introduced at the very beginning. So we have a smooth curve, gamma from I to M. I is an interval in R. And the length is L of gamma, defined as this integral from A to B of the norm of gamma dot T with respect to dt. The energy on the other side is, well, defined as E of gamma, 1/2 of the integral, and now we take a square here, square. That's difference. Okay. And we can discuss, so this is again a kind of small recap of what was seen previously. We can discuss the notion of variation of gamma. So we have a variation if gamma is a family of smooth curves, so indexed by S, gamma S maps I to M, well, such that the pair ST is mapped to gamma S of T. We want it to be smooth, and we want to decide that at time S equals 0, gamma of 0, well, gamma indexed by 0 is just gamma. So on the right-hand side of the slide, we can see red and blue curves. And what I'm doing here, so we can see them very slightly deforming. So there's curves that are, well, overlapping, but it's just to illustrate that we're deforming during time S for any gamma of 0, gamma 1, gamma 1.5, we're deforming all these curves. So we have the red deformation and a blue deformation. So that corresponds exactly to a polynomial. So there's an algebraic equation here. It is not just topological, it's also algebraic. And this is to illustrate that, well, although my speech is a little bit topological here, you can do it using deformations of coefficients of some real polynomials into two variables, harmonic type of polynomials. Right. So that's about varying a family of smooth curves, deforming them. And notice that the red curves are very, very close to intersecting, but they're not yet intersecting. So they're all isotopic here. All right. So now let's talk a little bit more about geodesics. So consider a smooth curve, gamma from I to M, where I is an interval from A to B and A is smaller than B. Then we have the following statements, which are equivalent. So every variation gamma S of gamma with fixed endpoints. So previously we can see that the one blue curve had really fixed endpoints, and a red curve also had different fixed endpoints. So every variation gamma S of gamma with fixed endpoints satisfies the equation d over ds when S tends to 0 of the energy has to be 0. So we have the extremal of the energy functional. And gamma is the extremal of the length functional too, actually. So that's d over ds for S equals to 0 of the length has to be 0. Now the third statement is that the velocity vector needs to be parallel. That means nabla of gamma dot t is 0. So that's one of the last slides we saw in lecture 2 about this parallelism notion. Nabla of gamma dot t is 0 for any t and I. And fourth, the acceleration of gamma is normal to m. That means double dot of gamma t has to be perpendicular to the tangent space to m at gamma of t. And this is true for any t and I. So to summarize, we have 4 different equivalent ways of describing the situation. And well, we can choose to define geodesics as follows. Gamma, the smooth curve, is a geodesic if and only if nabla of gamma dot t is equal to 0. And this is for any t and I. So now we know what it means to have a geodesic for Riemannian manifold. Right. So this obviously leads us to the notion of intrinsic distance. So I did a little picture at the beginning. It was here where I was drawing in green an Euclidean distance, and the pink was a intrinsic distance. And I wanted to highlight, well, that there's a great difference. So that's what we're going to discuss here. So assume M is a smooth manifold in the Euclidean space. All right. And now take 2 points, P and Q and M. And now, well, we can take just the most obvious distance with the ruler, the area of distance, norm of P minus Q in ambient Euclidean space. But what can we really say about the distance on M? So this question, to answer this question, we use the intrinsic distance in M. So let's define this. The intrinsic distance on a manifold M between 2 points on it is a real number, which is obviously positive, and defined as this infimum of the length L of gamma for gamma lying in a space of smooth paths of the unit interval joining P to Q. So we have a space of smooth paths joining 2 points, and well, the intrinsic distance will be the infimum of the length L of gamma. And that's it. So I think the picture here was quite clear. We're taking, maybe this was not the shortest length in pink, but it was a length. Okay. So a home exercise homework, we can prove that the length of gamma is necessarily greater or equal to the Euclidean distance p minus q. Okay. So now we have defined intrinsic distance geodesics on a manifold, Riemannian manifold. We can also add, this is not a crucial side of the talk here, but we can mention the existence of something called geodesic convexity. So given M a smooth M-dimensional manifold, we can take a subset U inside, and it is geodesically convex if and only if for all points P0, P1 in U, there exists a geodesic gamma from 0, 1 to U such that gamma of 0 is P0 and gamma of 1 is just P1. So I thought it's interesting in relation, for example, to cones and things like that. Okay, and so this leads us now to the notion of curvature. So the curvature is a very important notion in geometry. So we can see here on the left-hand side of the slide, there are two figures. One is just a sphere, well, or something that looks like a sphere. And next to it, there's a surface, which is a quadratic type of surface. And we can see that it does not look like a flat plane. And so that's all what curvature is about. So the curvature is the amount by which a surface deviates from being a plane. And I would like to draw attention on the right-hand side on the picture there. So it's a picture by Escher. So he drew a city. So that's the way we could see with perspective. That's the way our eye could see it on the left-hand side of the sketch. And next to it, there's his art, what he did from it. And it's like as if there was some kind of curvature. There is a kind of ball popping out in the middle. And I find it very interesting because, well, it's an illusion. So we're on a flat plane. And even though we're on a flat plane, so the picture is on a flat plane, well, there's an impression of curvature. So it's a projection on a plane of a structure that should have curvature, non-flat curvature, non-zero curvature. So I find it very interesting to compare this notion of curvature, so we're studying manifolds and everything, and put it in parallel with artistic, for example, projections, visions of what a curvature could be. So let's be more technical now. So the notion of curvature comes from the study of parallel transport on a surface. So now we're very far from artistic pictures. We're going back to parallel transport. And so we had, let's recall, a curve, for example, in a manifold, and we had a vector field, and we were, well, maybe transporting it from one point to another one. Now, the curvature here is crucial because if a vector is moved, for example, around a curve, which is a loop, so we start at point P, and the end point is again the point P, so it's a loop. If a vector is moved around a loop on the surface, for example, the sphere, because it is not flat, keeping parallel throughout the motion, then the final position of the vector may not be the same as the initial position of the vector. And so that's how it's born, actually, the notion of curvature. And I'm quite interested in discussing this on a planar projection such as Escher did, and maybe explaining what happens when you're just projecting something that should have curvature on something which is totally flat. So I think it's a good exercise to try to discuss this. So that is curvature. Right. So there are many ways of defining curvature. So the version I chose goes as follows. So first of all, I chose Riemannian curvature because we're talking about Riemannian manifolds and everything is Riemannian. So let's talk about Riemannian curvatures too. So let us consider a Riemannian manifold denoted as usual MG. Then the Riemannian curvature tensor is defined as the following map. So usually we call it R, and it is the space of vector fields on M times the vector fields on M, again vector field, 2 space of vector fields on M. And given by the formula that we see in the middle, so usually we take X, Y, and Z vector fields in M. And so R of X, Y, Z is, and now say hello again to nabla X. We have nabla X, nabla Y of Z, minus nabla Y, nabla X of Z, minus nabla of the commutator, so the Lie bracket here, of Z. So commutator, so the bracket, XY is a Lie bracket of vector fields. And again, bracket of nabla X, nabla Y is a commutator of differential operators. So that's, in fact, a very general type of definition for the curvature. And so note that the right-hand side only depends on the value of the vector fields X, Y, Z at a given point. Well, so in short, so I had a very visual introduction to curvature because it's supposed to, well, transmit something visual and geometric, but we can express it in a much more algebraic way. So the curvature tensor measures non-commutativity of the covariant derivative. So that's the more algebraic way of expressing things. Well, the advantage of algebra is that we can compute things and prove things much more easily than using just geometric intuition. Sometimes. All right. So this leads us to defining things in a slightly more global way. So here I will use maybe a little more of vector bundle language. If you're not familiar with it, it's not a problem. It's not so hard to introduce vector bundles and things like that. So for X, Y, Z, which are vector fields on M, I rewrote the formula. Rxyz is nabla X of nabla Y Z minus nabla Y of nabla X Z plus nabla of this commutator X, Y, Z. And using the language of bundles, the curvature of a connection, nabla on a vector bundle, so E to M, so M is your manifold and E is what they call a total space. So it can be, for example, if you have a tangent bundle, it will be Tm. And you have a trilinear map. So gamma stands for sections. So section means that you will go from M to E instead of E to M. And you have sections on Tm times sections on Tm. In other words, you have vector fields of gamma E into gamma E. So gamma is just section, and it means it's another way of defining how it gives another tool to define vector fields here. So that's a slightly more algebraic way of seeing things. So as a gemstone exercise, we can show that we can rewrite it. So this is not so hard. Rxy is just the bracket nabla X, nabla Y plus nabla of the bracket. Yes, I leave it as an exercise. It's just a question of calculation. Okay, so let's talk a bit about properties of this. So we have some symmetries. R of yx is equal to minus R of xy. So that's one thing. And then we have something a bit more sophisticated. So R of xy z plus R of yzx plus R of zxy is equal to 0. So it looks a little bit like this Jacobi identity. And finally, we have the last, not the last, but the third condition, which allows us to have a property for swapping the vector fields between each other in this context here. So, so that's the global formula for curvature. So we want to use it. Well, we want to explore a bit more this notion. So generalization includes scalar curvature, Ricci curvature. I will not mention them. I'll just focus on something a little bit different, which I'll not say immediately because I want to comment. So these are 3 gemstones for more sophisticated language appearing here. So as I said previously, we can think of a vector field as a section of a tangent bundle. So I could perhaps write something here. So if we have, so I like to think of the vector tangent bundles that way. So we have M a manifold, and there's the total space here. And then we have pi, which is the projection map. This is E here. It could be TM if we want. And the section, well, it's just a way of going the other way around, such that pi composed with S is the identity. So taking the tangent space here, we can think that, well, to a given point on M, we are attaching, well, in this case, a vector field because it will live in the tangent space TM. So that was an intuition explanation of what is hidden behind this bundle and behind the gamma M, or sections of the tangent bundles. So as I said, we can think of a vector field as a section of the tangent bundle, and we can denote it omega 0 M TM. So it's just a notation, which is just this vector field on M. So that's a given way of saying things. So, okay, so that's the vector fields. Then a second thing that I wanted to add is one form on M with values in a tangent bundle is a collection of linear maps from TPM into TPM, such that for every smooth vector field X in M, the following assignment, which to any point associates A of P XP, defines a smooth vector field in M. So that's a little bit more sophisticated, but that's a different way of thinking about one forms on M with values in the tangent bundle. And yeah, so the space of one forms on M with value in TM is omega 1, usually MTM. So so the notation omega comes from the work of topologists on exact sequences, short exact sequences. So it's like a standard notation used here. And finally, let's add something about covariant derivatives. So the covariant derivative of a vector field Y is such a one form with values in a tangent bundle, assigning to each point P and M the linear map. So it's exactly nabla V of your vector field Y at the point P. And V is a vector. So to conclude, we can think of the covariant derivative of this nabla from omega 0 mtm into omega 1 mtm. So this gives us here on the left hand side here, we have a vector field, and omega 1 will be exactly what we were explaining about these one forms and the covariant derivative. That was vector fields on M. So that was the more sophisticated side of the story. And yes, so I wanted to say a bit something about Riemannian metrics on Lie groups, because it's a good example to consider. And it's less intuitive than just drawing pictures of some donuts and spheres. So let's discuss that. So Riemannian metrics on Lie groups. So we consider a Lie subgroup G of the orthogonal group O of N. So it is compact. And what I find very interesting is the Riemannian metrics topic occurring for this situation. So we have a Riemannian metric inherited from the standard inner product. So here we go. We have this inner product. So it's the trace map here for you take matrix V transpose and another one W. Yeah, so that's inherited from the standard inner product on the ambient space, GL and R, is these matrices of size n. And then, well, this is more of something we already proved in some sense, or already saw, the Riemannian curvature tensor on G can be expressed in terms of the Lie bracket. So yeah, we could do this as an exercise. And furthermore, so that's really due to the beauty of Lie subgroups and Lie groups here, the maps, which map G to AG, or G to GA, or G to its inverse, or are isometries of the Lie subgroup G, any element A in G. So yeah, so it's a very interesting thing to discuss here about these Riemannian metrics on Lie groups, and there will be a whole bunch of exercises coming soon on this topic. But before we discuss this, let us talk about, let's be more theoretical about constant curvatures and sectional curvatures. So there's a very important notion of sectional curvature. So as the name says, there is a notion of a section, we're cutting, and there's a notion of the curvature. So let M be a smooth M-dimensional submanifold living in Rn, and let us take a point on the manifold. Now let us consider a two-dimensional linear space of the tangent space, denoted E. The sectional curvature of M at the point P and for this two-dimensional linear subspace is the following number. So it is expressed in blue here. KPE is this, this object that we can see here, where RPUV has been defined previously here. So it's the equation in the middle. You can highlight here. So U and V are vectors lying in the two-dimensional plane, E. They're linearly independent, and RP, as we said, is this Riemannian curvature tensor. And I think it is a very interesting exercise to consider matrices of size n, which are symmetric, positive, definite, and compute sectional curvature for this type of space. So we will see later on what this gives. By the way, does anyone have an idea of a sectional curvature for matrices which are symmetric and positive definite? Okay, we'll discuss it later. And so, okay, we have now a sectional curvature definition. There is also a notion of constant sectional curvature. So the definition is not extremely different in the sense that, well, we have a number k, small number k, and m is an integer greater than 2 or equal. We say that an m-dimensional manifold has constant sectional curvature k if and only if this sectional curvature KPE, so KPE here, is equal to small k for any point P and M and any two-dimensional linear subspace E of TPM. So essentially, we have to compute a sectional curvature for any point P and any two-dimensional linear subspace of the tangent space. And if they're always equal to the number k, well, then we have constant sectional curvature. So in other words, we have the following theorem. Let M in Rn be an m-dimensional manifold. And let us fix an element P in M. It's a point and a real number, small k. Then the following are equivalent. So we have that capital K PE, so the sectional curvature of M at P and E is equal to small k for any two-dimensional linear space E in TPM. And we can express the Riemannian curvature tensor of M at P given by the last equation here. So we see that we have taken V1, V2, V3, V4 vectors in the tangent space at a given point. And we want to compute, well, this evaluation here. And we see that there is K appearing here again. So essentially, we have these two statements here, which are expressing the notion of constant sectional curvature. And right, so we can discuss a little bit examples occurring there. So let's take the example of non-positive sectional curvature. So as the name indicates, we have the notion of sectional curvature, and it's supposed to be non-positive. So consider a Riemannian manifold M. It has non-positive sectional curvature if and only if capital K of PE is smaller or equal to 0 for every point P and M and every two-dimensional linear space E lying in the tangent space TPM. So we want in particular to have this inequality to be true. And this holds for any, well, every two-dimensional linear subspace. And then there's a definition which I find it interesting. It's that a non-empty connected, simply connected, complete Riemannian manifold with non-positive sectional curvature is what some call a Hadamard manifold. And so my question to you is, do you have any example of a space with non-positive sectional curvature? So I have a favorite example. And I can give a hint that, well, it's strongly related to linear algebra. So I'll let you think a bit about examples here. There are many, right? But okay. So my favorite case is the space of positive definite symmetric matrices. So maybe you've noticed all along the lecture, I have just picked essentially this case, not always, but in most of the cases, and I have developed questions all around it. So let M be a positive integer and consider the space calligraphy P, which is a space of matrices such that P transpose is equal to P, and such that, well, it is a positive definite. So we have this inequality here. For any non-zero vector x in Rm. So that's exactly the positive definite symmetric matrices of size M. Now let us notice something interesting, that it is a subspace of the space of symmetric matrices. Let us recall that symmetric matrices are matrices of a given size M such that S equals to S transpose. So in lecture 1 or 2, there was a question about, do we know what's the tangent space to the space of positive definite symmetric matrices? So here's a hint. In fact, the tangent space at a given point to the positive definite symmetric matrices is the space of symmetric matrices. So I find it very interesting. There are at least 2 different ways of proving it. One can pick their favorite way. And now there's a interesting computation about the Riemannian metric. So we were talking previously about an example. So it was here that Riemannian metric is inherited from the standard inner product. So we had inner product V with W is the trace of V transpose W. So maybe now you're going to tell me that, well, yes, but here we're talking about Lie groups, and you're talking about symmetric positive definite matrices. There is no relation. Well, there is a very strong relation, actually. So I'm not saying more about it for the moment, but one can bear in mind that we can define a Riemannian metric on the space of positive definite symmetric matrices as follows in this equation here. So we again have trace operator appearing, and we pick a matrix P in which is positive definite symmetric, and we take 2 other matrices P1 hat and P2 hat, which lie in the tangent space. That means symmetric matrices. And so the Riemannian metric is given, so for a given point, which is now our positive definite symmetric matrix, so that's our point here. We take 2 vectors in the tangent space. Well, vectors is now going to be 2 symmetric matrices, P1 hat, P2 hat, and the Riemannian metric is the trace of P1 hat, P inverse, P2 hat, P inverse. I'll just erase this. So that's the very interesting case of positive definite symmetric matrices. So I'm interested in it for the different reasons, but one can note that there are many applications of symmetric positive definite matrices in everyday life. For example, the first application is in optimization due to convex programming. So this appears very strongly there. But it has a whole very rich range of applications, for example, in information geometry and harmonic analysis, for example, via Wishart laws. And these are important in random matrix theory and statistics. So I'm just mentioning relations there. I am not developing all the story of how they appear there. I'm just mentioning keywords here now. And I can add also, well, that it appears in medicine. So there's a technical word which is diffusion tensor imaging. And so it is a model, it is used as a model of the anisotropic diffusion of water in the tissues. So it's quite important in fact, in medicine. And another application is in machine learning. So, for example, if one is interested in finding correlation between given properties, for example, one could take weight and volume or weight and height of people, one can model the relationship using a covariance matrix. So it is the last formula outlined on this slide. So it's here. Yeah, and many more. So that was just what I outlined, a few possible applications of this. And it is also very much interesting in pure mathematics. So before we discuss it further on, well, I can say that there is a strong relation, and that will be an exercise for you, to symmetric spaces, for example, and there's a strong relation to a quotient of Lie groups. And so that's what I want to say here in this slide here. So, so let's mention the following theorem. The space of positive symmetric definite matrices P with the Riemannian metric that I outlined 2 slides ago, so on the bottom, is connected, simply connected complete Riemannian manifold with, and here it was the solution to one of the exercises, non-positive sectional curvature. So that's an example of, well, a Riemannian manifold which has non-positive sectional curvature. So I'm going to underline this because this is very important. The non-positive sectional curvature. And we can add furthermore something about the distance function on that space, which is given as follows by this very impressive formula. So given two matrices P and Q, the distance between P and Q is given by this square root of the trace of the log of P, well, as you can see. And right, so the group GLMR, general linear group, acts by isometries as follows. So we take P in the space of positive definite symmetric matrices, and it is mapped to G transpose for any element in GLMR. So we have, well, we can see that there is a strong relation to Lie groups, which starts to appear. Okay. So I have outlined 2 exercises. Well, there's a very interesting exercise. So I was saying that we had traps in the exercise because I did not define every single notion, but they might be useful for solving the exercises. And I think it's a good homework to look for them by ourselves. So there's a very interesting statement which says that the submanifold P0 of the space of positive definite symmetric matrices with determinant 1 is totally geodesic. So that's a very interesting exercise to consider. And more accessible, I think, is to prove that the space of positive definite symmetric matrices P is diffeomorphic. So one can look at it in a different way as the quotient of two Lie groups, GLMR, quotient by orthogonal group, OM. And now if we just restrict attention to P0, well, prove that P0 is diffeomorphic to the quotient of SLMR over SOM, so special linear group quotiented by a special orthogonal group. So we see that we can range absolutely from applications which are extremely useful in everyday life. We can go from this to symmetric spaces, so pure mathematics, quotient of Lie groups. And I think the whole beauty of it resides in this. So extremely useful to be a champion in differential geometry. Right. So I think I've talked 55 minutes. If perhaps we could end the recording in case people want to discuss exercises and feel more at ease to express themselves. So welcome back to lecture number 4. In this lecture, we will get acquainted with level 5 and level 6 applications of geometry to information theory and beyond. So let's get started. So this side of the lecture is more connected to information theory. So we have probability theory interacting here. And I'll introduce it a little bit and discuss further development or actual developments. So in case people don't know what is a measure space, I will just recall it. So let omega f be a measure space where I denote f a sigma algebra of elements omega. And we consider a family of probabilities on omega f, where a probability is defined as follows. It is a map, usually denoted P, from F, the sigma algebra, into the interval 0, 1. And furthermore, we need to satisfy 3 axioms. So PA, where A is any element in the sigma algebra F, is contained between 0 and 1. So 0 is smaller or equal to PA, smaller or equal to 1. That's the first axiom. A second axiom is that P, so the probability of the entire omega, is equal to 1. So that's the second axiom. And thirdly, we have the following. So given any elements AI in F, sigma algebra, such that they do not overlap, so the intersection is empty between AI and AJ, then the probability of the union of AI is equal to the sum of probabilities of AI for any I, for I in natural numbers. And so that's defining a probability. So these 3 axioms being said, we will define a sigma finite measure lambda, where lambda is the map from F to 0 infinity. It is finite on all bounded subsets. So example is the Lebesgue measure on Rn. So that's the setting. That's first step. And now we need a second step, which is the density of a measure. So a measure P, or a probability measure P, is said to be absolutely continuous with respect to lambda. So lambda we defined just a few seconds ago. If for every measurable set A, lambda of A equals to 0. So measuring this, if it's equal to 0, then it implies that the measure P of this A has to be 0. So that means that a measure P is absolutely continuous with respect to another measure lambda. And this implies the existence of a measurable function rho, which is defined as follows. So P of A is equal to the integral on A of rho d lambda for any A in F. So let us comment a little bit on this. This is quite interesting because so rho is called the density of the measure P, but rho, if we want to play a little bit with it, can be identified to this derivative dp over d lambda, which is in fact a Radon-Nikodym derivative. So here we've said a whole bunch of very important things. So that's very important to understand, this density of the measure concept. And so now that we've said the most important here, we are allowed to define a manifold of probability distributions. So manifold we've been talking about in lecture 1. So now it is just a question of applying all these differential geometry tools to something, well, which is well, difficult to imagine, such as probability distributions. So consider a measurable space omega F, where F is a sigma algebra of omega. And now consider a family of parametrized probability distributions on that measurable space, omega F. So when I say parametrized probability distribution, it means that the probability depends on a family of parameters, real parameters, usually. And there's a property which is that the set of all probability distributions over a finite set and of a given family, given type, forms a manifold. Yes, on the right-hand side, I was thinking about the discrete case, and I was trying to, well, I asked artificial intelligence to draw something that could remind probability distributions over a finite set. So that's what it gave me. So that's the main concept we're interested in. So we have the manifold, we already saw it, and we're now seeing this from the eyes of information theory. So what I am specifically interested in is a specific case of manifolds of probability distributions, alias called statistical manifolds. I'm interested in the case where the probability distributions will be of so-called exponential type, an exponential family. And furthermore, I will require, so we had a whole bunch of discussions about connections and curvature and so on, and I will furthermore ask this manifold, well, I will ask the question when it is flat. So I will be looking at the case when it is flat, a flat statistical manifold of exponential type. What does it mean to be of exponential type? Well, it means that probability distributions, so the rho theta, can always be expressed, if we choose correctly parameters and random variables, can always be expressed as exponential of the sum theta I xi minus a function psi of theta, where psi of theta is what we call a potential function and satisfies some very rigorous properties, which for simplicity I will just omit. So that's what we call an exponential family, or having probabilities of exponential type, probability distributions of exponential type. So as I said, parametric families of probability distributions of exponential type form a manifold, a smooth manifold usually, and I'm interested in asking about its flatness. Is it flat? When is it flat? What's the condition for it to be flat, etc. So what is it exactly that we're doing? So let us consider the manifold of probability densities. So what am I considering as object is the following. It's a family of probability densities of parametric probability measures, which is denoted as follows. So instead of M, I choose S. So it's the set of rho thetas, which are in fact L1 functions on omega F. And we choose lambda as before, such that rho is positive, and we have some other condition on lambda, plus the fact that integral of over omega of rho is 1. And we want to consider the case when S is a smooth topological manifold. So that's going to be our manifold, this S that I outlined just in this line here. So, so exponential families go as follows. So probability distribution and statistical manifold of exponential type are such that there exists parameterization theta satisfying this equation. This formula, rho theta is exponential of the sum theta I xi minus psi of theta. Psi of theta is a potential function, and we have to choose theta correctly. And we will discuss this problem in a few seconds, how to choose theta correctly. Well, let's take an example at first. So as I mentioned previously, the question is whether or not a family of probability distributions is an exponential family. It's actually not always clear. And I want to draw your attention on the case of the normal family, and with its very classical type of parametrization. So let's recall that normal, or they're also called Gaussian distributions, are defined as follows. So the probability distribution with respect to Lebesgue measure on R is, as I wrote down, rho, and the parameter here is the expected value, mu, and the variance, sigma. And it is given by 1 over square root of 2 pi and sigma, exponential of this quotient. So mu is the expected value, it's a real number, and sigma is going to be variance, and it's going to be a positive number. And so from Wikipedia, we can see that curves for different values of expected values and variance behave as the colorful curves we see on the screen. Green, yellow, red, and blue. So my question to you is the normal family an exponential family? So that's worth 2 gemstones, because it's actually, I would say, not so easy to rewrite it in the shape that we've seen here, rho theta exponential of a sum minus psi. So the answer to this is given in this slide. So it's the normal family exponential. And well, we have to work a little bit, and this reparametrization is not as elegant as the previous one. So let's choose, for the case of the normal family, the following parametrization. We have theta, theta 1, theta 2, where theta 1 is the quotient of mu by sigma square, and theta 2 is minus 1 over 2 sigma square. Furthermore, we can compute that the potential function here, psi of theta, is 1/2 of ln of minus pi over theta 2 minus theta 1 squared over 4 theta 2. So this requires a little bit of work to manage to write it in this shape. And now you can check by hand that the normal probability distribution density is indeed rho theta x exponential of theta 1 x plus theta 2 square x square minus psi theta. And this is thus an exponential family. That's what we wanted. See here in the formula. So the normal family is an exponential family. We can discuss now a little bit about charts, because charts are tightly related to manifolds. So I was mentioning a manifold of probability distributions. So let's discuss a little bit the chart story. How does this work? So first, one thing to understand is the point on our statistical manifold S will be in fact a probability distribution. And we said that they are parametric probability distributions. So in particular, they are indexed by theta. Theta lies in Rn. And theta form, in fact, the coordinates. So I did a picture on the bottom. S is the manifold of probability distribution. I took a point, which is a probability distribution, and an open set around it, ui in red. And I wanted to define the charts and the coordinates. And we see that it lies in Rn with this theta being coordinates. So a little bit about the chart and atlas. So given calligraphy U, I, an open set in S, and phi I, a chart which will map calligraphy UI into an open set of Rn, so it's straight U. So that will be our chart, and phi will map, well, the probability distribution, rho theta, to theta, its coordinates. Everything, I think, is quite natural here. But it's important to mention regarding the fact that we have now probability distributions, and it's not evident what happens. Right, so we can talk about charts for normal families to give a concrete example of what's going on. So, as I said, if we take the normal, or also called Gaussian families, so we have this normal distribution parameterized by mu and sigma, where mu is the expected value, which is a real number, and sigma is positive, so from a number from 0 to plus infinity, where 0 is not included. So this defines, in fact, a two-dimensional space of parameters, which is the open upper half plane. So it's the yellow, the yellow color on this chart here. So we have the upper half plane. And now I would like to draw attention on the fact that the atlas has only one open set. The one open set is nothing but the open half plane with chart associated to the mu sigma coordinates. So this two-dimensional statistical manifold can be associated to a Gaussian manifold defined by a single atlas with coordinate mu sigma. So it can be identified with the upper half plane. Mu lies in R and sigma is strictly positive. So that's the beauty of the normal family here. So as a remark, and maybe as a dangerous step, we could try to use the canonical chart, the one that served to, it's an exponential family, and see what happens considering the charts and the atlas. And I think it would lead to more complications. So I put a warning sign. It will be much more complicated. So sometimes the good step is just to take the most easy chart, what is more convenient for us. So we talked about the manifold structure of this statistical manifold. A natural question now to ask is about the tangent space. How does it really look like? Is it a bit exotic, or is it visual, or is it completely strange? So let's talk about the tangent space to the manifold of probability distributions. So here we go. Let U be a L2 function. So it will be a tangent vector to the manifold of probability distributions S at a given point P theta. Of course, I'm looking only at manifolds of finite dimension. Then the tangent space T theta is defined as follows. We consider the set of tangent vectors U, so L2 functions on omega f, fixed at a point P theta, with expected value of U equals to 0. And furthermore, we can express U in a given basis, which is partial I L theta. I will define it in a few seconds. So let us mention that the tangent space of S is in fact isomorphic to the n-dimensional linear space generated by what we call in statistics centered random variables, also called score vector, and which are generated in the basis partial I L theta, where L theta is the log of rho theta, ln of rho theta. So that's how we define this tangent space. Let's remark the following. So densities are positive random variables almost everywhere, and tangent vectors are what we call signed measures. So it's a real valued measure with vanishing mean value. So that's all about tangent spaces. So I wanted just to make an easy calculation on why the expected value should be 0. So it is not so hard to see that this is true. So well, let's pick our first definition. We take the integral over any element A in the sigma algebra F, integral over A of rho theta. And well, we just apply the definition actually. So derivative of p theta in the direction theta I is just the integral of, again, a derivative. And then, well, maybe I could write. Okay, so now that's the first step. That's by definition. So that's definition. And now, well, we just multiply and divide by rho theta, because it allows us to define the, well, derivative of the log. That's just definition of derivative of the log. So it gives us this. And well, now we just use the definition, well, the axiom that we saw at the very beginning here. And the definition of the expectation of the mean value here. And we see that it's just 0. So given that U is a linear combination of these partial I L theta, well, it's just 0, everything. Okay. So that was the calculation about why is it so that expected value should be 0. So let's take again our favorite example of normal families. And here we can compute the tangent space of normal families. So we saw it's a two-dimensional manifold. So the tangent space is spanned by two random variables. And we can compute them. So it's partial mu of ln rho, partial sigma. So it's derivative in direction mu and derivative in direction sigma of ln rho. And we can compute, so that's an easy computation actually. Sorry, it doesn't want to work now. So yeah, it's an easy computation that we can check by ourselves, that in direction mu, it corresponds to x minus mu and sigma square. And well, for the direction sigma, the derivative of ln of rho is, well, x minus mu square over sigma cube minus 1 over sigma. So that's just a direct computation. And so therefore, well, by a nice change of variables, we can see that the tangent space consists of quadratic polynomials in x whose expectation vanishes. So in other words, we can write it as being ax squared plus bx plus c, such that c is a times sigma squared plus mu squared minus b mu. And a, b, c, well, a, b are just coefficients that you can choose well, to get this shape. So that's just easy computation here. So that was about the tangent space of normal families. So we can go quickly to the metrics. We have, it's a Riemannian manifold. We have a Riemannian metric, which is, well, was introduced by Fisher-Rao as a covariance matrix of the score vector. So Gij is this expected value at this point, p theta, of, well, partial I L theta, partial J L theta. And there's the inverse version where AI are just, well, naturally a dual basis of the basis partial J L theta. And that's like, yeah, so that's to say that there exists a Riemannian metric. So we have a Riemannian manifold. So I'll maybe speed up because otherwise we won't have time to see the level 6, which is the most exciting, I think, of today's course. So, okay, in a few words, I can just say that, well, we have a Riemannian manifold and we can use all the differential geometry we've been, considering in the lectures, parallel transport, affine connections. You can do everything here with Christoffel symbols, moreover. So that's just to say that you can do a parallel transport. So here I was defining in detail, in great detail, what's happening here. You see connections, covariant derivatives start popping up here. And also our favorite coefficients, the Christoffel symbols. So that's just a definition of affine connections. We see you have linearity on vector fields b plus b prime or a plus a prime. Everything is behaving very nicely, linearity conditions. And there's like an object which will play a huge role in the level 6. It's the Amari-Chen-Soft tensor, so also called a skewness tensor in the literature. So we have a rank 3 symmetric covariant tensor, I denoted here T. So from the tangent space times tangent space times tangent space into R, and which again uses the expected value, the mean value, expected value of UVW, or partial I in the basis we have defined for the tangent space. So partial I L theta, direction J, and direction K of L theta. So that's extremely important as well, geometrically speaking as statistically speaking. And well, it was introduced as a way to formalize the notion of statistical curvature via the affine connection. So hugely important to calculate the statistical curvature here. So we have this beautiful formula in the middle of the slide here expressing curvature, well, connections and thus curvature, and which is defined for any vector field xy over S. And nabla 0 here is our Levi-Civita connection. And the dot here stands for a contraction of two tensors. So we have T bar. And so from literature and ourselves, we can compute coefficients of the affine connection. So it's this purple formula on the top of the slide, gamma ijk alpha, where alpha is a given parameter, a real parameter. And we call this an alpha connection. So in fact, this is used furthermore here to calculate well, the alpha connection via, well, the Amari-Chen-Soft tensor. So you see we have a huge simplification from formula on the top, gamma ijk alpha, to the formula on the bottom, also in purple. And you see that we use Tijk, which is the Amari-Chen-Soft tensor, and simplifies greatly, well, the beauty of the formula and thus the calculations. So the alpha connection, except from being very useful in geometry, has a meaning of its own. It plays, for example, a huge role in statistical inference. So it's interesting, it's in its own right. And in the next part, I will be interested in statistical manifolds or submanifolds of exponential family, which are flat. So curvature is 0 flat. And so I put a little skull here because we're navigating furthermore to wild topics, which may be a bit dangerous. So just concerning our little game of collecting gemstones, if you manage to collect more than 30 gemstones, then congratulations. And you will see hidden sides appearing of level 6, which I'll be mentioning right now. And if not, well, you can try again and train until we collect enough gemstones to see hidden sides of level 6 appearing. So level 6. So this is a very exciting part related to recent results of mine. And so things go as follows. So like the development and formalization of topological field theory, including the very famous mirror conjecture, led to well, creation of all sorts of mathematical tools, and in particular among them there are the notion of Frobenius manifolds. So Frobenius manifolds were not always called Frobenius manifolds because they correspond, in fact, to a geometrization of what people in physics call the WDVV PDE equation. So Witten-Digraph-Verlinde equation. So the Frobenius manifold name appeared as a development on the side of pure mathematics to give a more geometric concept to PDE equation named after WDVV, Witten-Digraph-Verlinde. And yeah. So let's say a few words about how all this appeared. So in the 80s, 90s, well, there's starting to be a huge breakthrough in all this topological field theory and a very fruitful interaction between algebraic geometers and theoretical physics, mathematical physics and theoretical physics. So the popularity of Frobenius manifolds among algebraic and analytic geometers was growing after an initial discovery of 3 large classes of them, well, which naturally arise in mathematics and also in physics. So a first class was what we call the Saitos framework. So for the physicist, it is related to Landau-Ginzburg models. For the pure algebraic geometers, it is an unfolding, well, it's a space of unfolding of singularities of a very special type. And the most simple example is the case of complex polynomial in one variable. Z is mapped to z power n plus and all the monomials of smaller degree. So, and that forms a Frobenius manifold, so satisfies WDVV equation. So that's one side, algebraic geometric side. Then there are very important other very important sides, which are, well, included mirror symmetry relations. So from the mathematical point of view, this led to a formal moduli space of solutions to Maurer-Cartan equations, modulo some gauge equivalence. And, well, quantum cohomology, the formal completion at 0 of the cohomology space of any smooth projective or symplectic manifold. So that's quantum space theory and its counterpart modulo this mirror, so the other side of the mirror. And so there was this, my contribution, flat manifolds of probability distribution of exponential type, which joined the club of Frobenius manifolds, and it's a very exciting problem to discover maybe new classes. So that's all very actual, very ongoing. And I would like to talk a little bit about hidden patterns of Frobenius manifolds and algebras in this information theory context. So before we start, there's going to be a whole bunch of more geometric definitions, especially concerning Frobenius manifolds, because it's, well, it should be introduced since we're talking about them. And I want to mention the little devil hiding in the details. So there was one little devil hiding in a given detail, which is the notion of affine flat structures, which well, has led to many, well, to confusion and to very strange discussions also. So I'll just recall what that means, and it's not so innocent. So we have to bear this in mind. So let M be a smooth M-dimensional manifold, and affine flat structure can be, well, defined in different ways. In particular, one which is very important for us is the following. Affine flat structures on M are in correspondence with a certain class of connections on the tangent bundle of M. More precisely, there is a bijective correspondence of affine structures on a manifold M and flat torsion-free affine connections nabla on M. So that's where the devil was hiding. Affine structures and bijective correspondence with the flat torsion-free affine connections. So I outlined a kind of example, which is a little bit of a definition too. So given a smooth M-dimensional manifold, we can notice that in the smooth or analytic case, an affine flat structure can be described by complete atlas. So say hello to lecture 1, whose transition functions are affine linear. And I recalled how it looks, sorry, the group of affine transformations. So it is this set of matrices A, B0, 1, where A belongs to GLN R, and B is a vector in Rn. So that's the very mysterious story about affine flat structures. So going back a little bit to lecture 3 and 4, we can talk about torsion-free and flat connections. So we mentioned something with Lie brackets. So here we go. Consider the Lie algebra of all differentiable vector fields on M. The affine connection nabla is called torsion-free if the following equality is satisfied. So nabla x of y minus nabla y of x minus the bracket, Lie bracket xy should be 0. That means it's torsion-free. And the connection is flat, so this is exactly the definition for the curvature that we visited on lecture 3, and which says the nabla x, nabla y minus nabla y, nabla x minus nabla of the commutator has to be 0. So that's the definition of being flat, essentially. And such a connection defines a covariant differentiation. Nabla x from vector fields on M to vector fields on M, or mapping a vector field y to nabla x of y for a given other vector field in another direction, for example, x in vector. So our knowledge is almost complete about affine structures, and here is a little comment about them because they're quite interesting. So notice that in the two-dimensional case, the torus and the Klein bottle are the only compact two-dimensional manifold that can be given Euclidean structures. And in particular, if we have a closed two-dimensional manifold which is not a torus or a Klein bottle, then there exists no affine structure. And so there's a theorem from 55 which says that a closed surface admits affine structures if and only if its Euler characteristic vanishes. So that's why I was saying that the little devil hides there, because it's not so easy to have a criterion for the existence of affine structures. In particular, for higher dimensions, there is no such criterion. Although there have been some results, and for example, a first case can be considered like this: a closed manifold does not admit an affine structure if its fundamental group is built up out of finite groups by taking free products, direct products, and finite extensions. So a connected sum of closed manifolds with finite fundamental groups admits no affine structure. So that's one thing I wanted to really highlight, that there is no criterion whatsoever, no real criterion. And for people who are more topological, we can mention this case that if M is a Seifert fiber space with vanishing first Betti number, then M does not admit any affine structure. So it's not so easy to guess if we have an affine flat structure or not. So I'm almost running out of time, but let's say things a bit quickly. So there is a more sophisticated language to express affine flat structures on M. So we can talk about sheaves and subsheaves instead of bundles, and we can consider a subsheaf. If you don't like sheaves, don't worry. Well, but there exists a subsheaf TMF of linear spaces of pairwise commuting vector fields such that TM is the sheaf of holomorphic functions, OM, tensor, TMF, over given ground field for R or complex numbers usually. And sections of TMF are flat, what we call flat vector fields. And I was talking in some given slide about compatibility of a metric, in case of the Levi-Civita case connection. And we want here exactly that the metric G is compatible with the structure TMF, which means that G of XY is constant for flat vector field X and Y. So that's a more sophisticated way of expressing things. But for a pre-Frobenius manifold, so it's not yet Frobenius, we're pre-Frobenius, we need an affine flat structure. We need a Riemannian metric, or let's say a metric, which will be compatible with the affine flat structure. We need an even symmetric rank 3 tensor A. We need a multiplication on the tangent space and some relations between A and G and multiplication. That means rank 3 symmetric tensor A of XYZ is going to be G of X times Y, comma Z, which is equal to G of X, comma Y times Z. And that all gives you pre-Frobenius. Now to get a Frobenius, you just need to satisfy two more axioms. You need to have a potential pre-Frobenius manifold. So it means that you need to have a family of local potentials such that for any local flat tangent field XYZ, this equality is satisfied. So A of XYZ is the derivative of phi in direction X, Y, and Z. And you need some associativity for the multiplication. So in particular, well, associativity means what it means. So we have X, Y, Z is equal to this. This associativity is in fact the heart of everything. So associative plus potential pre-Frobenius means Frobenius. That's a Frobenius manifold. And yeah, so I put a little symbol of skull and diamond because there are some relations in literature to free energy, but I will not talk more about this. Okay. So here I wanted to tell you that, well, with this more geometric version, you can find the WDVV equation again without problem. It's enough to, well, understand the compatibility of phi and G, that this will mean that partial of A times partial of B, so that is the sum of phi AB with the C on the top, partial C, and, well, that you can define phi of ABC in the following way here that I have outlined. And it becomes more of a, I don't know, exercise for a student to check that associativity holds and that indeed we get the WDVV equation. So rewriting the associativity with the steps I have outlined here leads, in fact, to obtaining a nonlinear system of associativity equations, which is the WDVV equation outlined in the middle. So that's how we stepped back to WDVV equation. So the more geometric vision of the story goes as follows. So we have MGA pre-Frobenius manifold, and we have a connection that is denoted nabla 0, determined by the condition that flat vector fields are supposed to be nabla 0 horizontal. So nabla 0 of a flat vector field is going to be 0. That's what means horizontal. And we have a pencil of connections depending on an even parameter. So we're deforming nabla 0 modulo a given parameter lambda times an element of the algebra in the tangent space, X circle Y, X times Y. I just want to draw attention on the fact that this tangent space with this multiplication and yeah, is in fact a Frobenius algebra. That's how you get connections to two-dimensional topological field theory. So the flatness connection, well, we have a flatness condition is issued from a theorem that we can find, for example, in the book of Riemannian. Let nabla lambda be the structure connection of a pre-Frobenius manifold, MGA. Then MGA is Frobenius if and only if nabla lambda is flat. Nabla lambda is here. Nabla lambda has to be flat. And we have to have a pre-Frobenius structure. And if all this holds, then we are Frobenius. So I just want to, in the following 2 minutes, I just want to explain how we see Frobenius manifolds appearing on the statistical side. So we have an emergence of hidden structures. The mixed tensor here, 2 covariant, 1 contravariant, is given by T bar ijk. It is the sum of this G with, so it's the inverse of the classical Riemannian metric here, so GKM with this Amari-Chentzov tensor Tijm here. So T bar ijk is just this expected value of, well, what we see here, partial I L theta, partial J L theta, and A theta K is the dual kind of vector. So why am I saying this? Well, for the simple reason that the key to have a multiplication structure resides in this object. The multiplication U times V, U circle V, is going to be given by T bar of UV. So T bar UV plays a very big key role in the definition of the multiplication on the tangent space. And in particular, we can check that G of U times V, comma W is equal to G of U, comma V times W. So we have all ingredients which are satisfied to get a statistical manifold of exponential type, provided that we are flat. So that's the next condition, that we want it to be flat. So it's not always flat, because in general it will just be pre-Frobenius, but from the moment where you restrict attention to flat statistical manifold, it becomes Frobenius. And so as a deadly, very hard exercise, we can prove again that we have a flat statistical manifold of exponential type, we have a Frobenius structure, and I have listed everything that's necessary to do it here on this slide here. I remind that the statistical manifold is a finite dimension. And this is it. So I just wanted to say that next week there is conference of geometric science of information, where I'll be talking about new developments on a more Poisson geometry side of this. So that was a result for 2020 about Frobenius manifold and statistical manifolds, and the research never sleeps, it continues. So next week I will be explaining new recent developments. And I want to thank you for your attention. I was very happy to make this lecture. I hope you enjoyed.